Hello, I would like to welcome you to lecture 25 of 3N03. We'll discuss in this lecture more applications regarding bipolar junction transistors. We'll discuss load line analysis, different operating regions, and I will give you some examples on these operating regions. We start first by considering the circuit shown here. This is a typical circuit for biasing a bipolar junction transistor. We have a certain supply VCC connected to the resistor RC and RE here as shown, and we have another voltage source that we use to bias the base emitter junction. As we have explained before, for the case of FETs, you can find the solution of the currents and voltages everywhere, either analytically or graphically. Graphically, we have to intersect what we call the load line with the characteristics of the transistor. So let's take a look here. This is the collector characteristics. So this one shows you the relationship between VCE and the collector current, and this is what this one here done for different base currents. So if I try to plot this one for you here, let me just show you the base current. So this will be for a certain base current, small base current, and then as you increase the base current, you get the current, the collector current start to increase, and so on. So the base current increases this way, and each one of these curves, this curve, this curve, this curve, and so on, represents the relationship between I collector and VCE for different values of I base. And the higher the value of I base, the higher the value of the current for the collector. So this is the relationship that we have between the collector and the I collector and VCE. VCE is the collector emitter voltage here. We can get another relationship between them using this loop. We have this loop here for the transistor. So this loop is simply telling me that VCC is equal to I collector R collector plus VCE plus I emitter R emitter. But as I explained for you before in lectures and tutorials, I emitter is nothing but I collector plus I base. But I base is very small. If beta usually is very high, so I base is very small. So effectively, I emitter is very close to I collector. So to be able to simplify the analysis, we can simply write the equation relating these two as follows: that VCC is equal to I collector multiplied by R emitter plus R collector plus VCE. So this is the relationship that we have between the collector emitter VCE and the I collector. This is the equation of a line. VCC is given, R emitter is given, R collector is given. This is the equation of a line where IC represents the y-axis and VCE represents the x-axis. If you make I collector equal to 0, you get VCC. So this gives you this point here on your graph. Okay, if you make VCE equal to 0, you get I collector equal to VCC over RE plus RC. So this point, this is this point here. This is a point on the y-axis, and your operating point can be really anywhere in between these two lines, because I collector and VCE, they have to satisfy the equation of this line here. This is this equation, and this is the equation of this line. Then what is our point of operation? Our point of operation is the intersection of this line with the corresponding characteristic, which has a certain base current. Okay, so we have to intersect them both, and we do this intersection all the time, either analytically by solving two equations, or graphically by simply drawing the characteristics for the base current, for the given base current, and we can find the base current. It's not that difficult. It's VBB minus 0.7 divided over RB plus, actually we have to actually take into account this drop here. So we can simply say that VBB is equal to IBRB plus VBE plus I emitter R emitter. But I emitter is equal to beta plus 1 multiplied by IB. So I can obtain only one equation in terms of IB, and then I can solve for IB. So for a given bias condition here, for the given VBB, for a given RB and given RE, I can exactly find what is the value of IB, because I emitter and IB base are not really independent. They are related by the ratio of beta DC plus 1. So now, depending on the current flowing into the base, we will determine which characteristic we are in, and then we intersect it with the load line. This can give us this operating point, or this operating point, or this operating point, or this operating point, or this operating point. It depends on the value of the base current. You can see if the base current is equal to 0, then we intersect the curve here. When base current is equal to 0 means that we have a flat characteristic. The collector current is 0, so this means the transistor is off, is cut off. So this means no current is flowing here. I collector is equal to 0. All the battery voltage will appear across collector emitter. No drop here, no drop here. And this is the case that we have here. In this case, it looks like an open switch. There is no current flowing. There is no I collector. There is no I emitter. VCC appears as a whole across the collector emitter terminals. This is the first case, so when there is no base current. Now, when we increase the base current gradually and slowly, maybe by changing VBB, then we are moving along this point here, which is in the forward active region. Both junctions are the base emitter junction is forward biased, the collector base junction is reverse biased. If I change IB, if I make the base current higher, I can move to this operating point. Okay, this is the intersection of my load line and this characteristic. If I change IB to IB3, I get this characteristic, and this becomes my operating point, and so on. We are all here still in the active region, but if you make IB too large, then the relationship that I collector is equal to alpha IB cannot be satisfied anymore, and you enter into the saturation region here. You can see we are not in the flat part of the characteristic anymore. We are at this point. And in this region, we call this region saturation region, as I explained earlier. This is different from the saturation region we had for FETs. This saturation region is characterized by very small drop between the collector and the emitter. So the voltage VCE will be below 0.7 as we agreed earlier, but it is usually a small number. Usually, and I will give you this number for simple calculations. We call it VCE SAT. This, as shown here, is called VCE SAT. VCE SAT can be 0.1 volts, can be 0.2 volts, it can be 0 volts. So I'm going to give you this one, and this will help us simplify the analysis. So as we agreed, we try to solve the load line with the characteristic of the transistor. The first region of operation, cutoff. No currents flowing as shown here. Now let's move the next slide to discuss the other regions of operation. Okay, if your load line intersects with your characteristic, the current is too high, I base is too high, then your load line will intersect with the characteristic here, not in the flat part, but rather on the saturation region part. So this region, as I said, is characterized by very small drop between the collector and the emitter. In this region, the transistor effectively represents pretty much short circuit. It represents a closed switch. So in order to analyze the circuit in this case, we say that VCE is equal to VCE SAT. VCE SAT is usually a small number. As you can see here, it's maybe around 0.1, 0.2 volts, and there is actually exact expressions you can find this VCE SAT. And once we know VCE SAT, we can go back to our circuit. We can simply say that the collector current from the outer loop is equal to VCC minus VCE SAT divided by R emitter plus I collector. Remember that I got this expression here from assuming that the collector and the emitter currents are the same. I ignored here the base current. Of course, you can approximate it further if VCE SAT is very small. Sometimes I give it as 0.1 volts or 0 volts. You can ignore this one, and this becomes VCC over RC plus RE. So this is the collector saturation current. Okay, this is the collector saturation current, and we can define something called base saturation current, which is equal to collector saturation current over beta DC. This becomes really a reference for determining whether we are at saturation or not. So once we determine the base saturation current, this is a reference. Then we determine the actual base current. If the base current is higher than this one, then we are indeed in the saturation region. Or the base current is less than this threshold, then we are still in the forward active region. And I will show you more examples on that. But this is the way that we usually use to analyze the problem analytically. So graphically, you intersect your line with the characteristic curve, determine VCE, determine IC, and we are done. Okay, analytically you assume VCE sat, usually a small number, because as I said, in the saturation region the transistor pretty much acts like a closed switch. Find the collector current, and this will give you a corresponding threshold for the base current, and then you compare your base current against this threshold to confirm that you are indeed in the saturation region. If your base current is higher than the threshold current, then we are okay, we are in the saturation region. Otherwise, we may be in the forward active region, or we may be in the cutoff region. The active region is the third case, which is the region between the cutoff and the saturation. You can see all this region is an active region. How would you characterize it? Simply the load line intersects the characteristic with the almost horizontal part, with the almost flat part of it. So here, 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 here. Once you get into this steep part, which characterizes the saturation region, then you are not in the active region anymore. And in the active region, I've shown you how to simplify this. We can simply find the base current. Once we know the base current, we can find the collector current. It is equal to beta IB. So this equation, I collector equal to beta DC IB, is only valid in the forward active region, in this flat part here. And once you know that, you can indeed verify that you are in the forward active region by checking VCE analytically. By checking VCE analytically, VCE is equal to VCC minus I collector multiplied by R collector plus R emitter. And again, I'm warning you here that I made the assumption that I collector is approximately equal to I emitter. Because to be accurate, this has to be VCE is equal to VCC minus I collector minus I emitter, R emitter. Okay, but here I'm taking into account that usually the base current is very small, usually micro amperes, while the collector and the emitter currents are way higher in value. So this curve, or this table shows us all possible regions of operation for the transistor, and what is happening for every quantity or every junction. So first, for the let's take region by region. In the cutoff region, both the base emitter junction and the base collector junction are reverse biased. Then the transistor is off. No current can flow here. Okay, so in this case, no base current is flowing in, no collector current is flowing in. The transistor looks like an open switch, so the complete supply voltage appears across the collector emitter probes or junction or electrodes. In that case, we use the transistor as an open switch. Okay, and this is used mainly for digital circuits. We use this open switch or closed switch. The second region of operation is the active region, forward active region. The base emitter junction is forward biased, as I explained earlier. The base collector junction is reverse biased. The base current is small and it's less than the saturation base current, which we can determine. The relationship between the collector current and the base current in this region is simply that I collector is equal to beta DC I base. I can find VCE as a verification. VCE is equal to VCC minus I collector R collector minus I emitter R emitter. But as I explained earlier, we approximate I collector. We said approximately I collector is equal to I emitter because the base current is small. And the last one, as an application, we use this region of operation. We use the transistor as an amplifier, and I will show you many examples of that. Why do you use as an amplifier? Because if you have tiny change in the base current, you have huge beta, so this transfers into large change in the collector current, and then we can convert very small voltage variation at the base to large voltage variation in the collector emitter junction. Now the last region of operation that we are interested in is called the saturation region. Saturation region, the base emitter junction is forward biased, the base collector junction is forward biased, and this means, for this to happen, this means that the collector emitter voltage has to be below 0.7. Okay, and usually what we do, we select VCE to have a certain VCE sat. It's usually a small number, 0.1, 0.2. We analyze the circuit to determine the current flowing in the transistor in saturation region. It's called the IC sat. And this gives us, of course, once we know IC sat, we can determine the base current, and this base current will be greater than the IB sat as well. Okay, IB can determine from the circuit. IB sat is a threshold. IB sat is simply equal to I collector divided by beta. So we find the base current. If the base current is greater than the threshold, then we are in the saturation region. It is less than the threshold, we are in the active region. We use this region of operation where the transistor represents very small voltage drop between the collector and the emitter, meaning very small impedance. We use as a closed switch. And these two regions, the cutoff and the closed switch, we use them to implement logic gates, and, or, nor, inverters, and so on. And I will show you many examples on how we can use bipolar junction transistors to implement these logic gates. Okay, let's take a look at an example here. We have this transistor that has beta equal to 50. At this 1 kilo ohm, R collector is 1 kilo ohm. There is no R emitter here. R base equal to 10 kilo ohm, and we are biasing the base through a 3 volt source. We would like to determine whether this transistor is in saturation or not, and we'll take VCE sat to be 0.3 volts. As we agreed, VCE sat is simply the voltage drop across the collector and the emitter when it's saturated, and we can determine this one exactly, but we usually select a small number. It does not really make big difference in calculations. To simplify the analysis, we take it as 0.1, 0.2, or 0.3. I will let you know exactly which value you should use. Okay, so what we're going to be assuming now, assume the voltage drop between here and here, between the collector and the emitter, is 0.3. If you have this 0.3, then I can determine the collector current, and the collector current is simply flowing this way. This is I collector here. So we can say that I collector is simply equal to 10 minus VCE sat divided by 1K. This will give me I collector saturation, I collector at saturation. We can determine from that VIB at saturation, which is I collector at saturation divided by beta, which is simply a threshold. Can we find the exact IB? Yes, of course we can find the exact IB if this is the base current. So we know that in saturation the base emitter junction is forward biased, so this 0.7. So the base current in this case is equal to 3 minus 0.7 divided by 10K. I can determine the base current. I will compare my base current against the threshold. If it is higher than the threshold, then I am indeed in the saturation region. If it's lower than the threshold, then I'm still in the forward active region. Okay, so these are the steps that we mentioned earlier. I assumed VCE sat between the collector and the emitter, so I assume that I am in the saturation region. I found the collector current, in that case we call it RC sat. It's VCC minus VCE sat divided by RC. It's simply obtained from this loop. So this is 10, this is 0.3, and the RC is 1K. You get 9.7 milliampere. Now, this gives us a threshold. This is not the value of I base. This is simply a threshold. Then IB saturation is I collector saturation divided by B DC. So this is 9.7 milliampere divided by beta, which is a big number. You get 0.194 milliampere. This is simply a reference, a threshold. Now we have to go back and calculate the actual I base. And as we have seen from the characteristics, if I base exceeds the threshold, then we are in the saturation region. If it is less than this threshold, then we are in the forward active region. So I base is simply equal to 3 minus 0.7 divided by 10K, and then we compare it with this number. So this what we do here. This is IB is equal to VBB minus 0.7 is RB. 3 minus 0.7 over 10K, you get 0.23 milliampere. Okay, so the base current is 0.23 milliampere, but the threshold was 0.19 milliampere. So this is telling us that our actual base current is higher than the saturation. Then we are already indeed in the saturation region. The transistor cannot be in the forward active region. So my operating point here in this case, or my Q point, or my quiescent point, it has many names, is that I collector is equal to I collector saturation is 9.7 milliampere. VCE is equal to VCE saturation 0.3 volts, and the I base in this case is 0.23 milliampere. I would like you to repeat this example again by assuming the forward active region, because it's very good to do that. Go back to this same circuit. Maybe we can try to draw it for you here. If I draw my transistor, okay, I would like to go back to this circuit again and assume that I am in the forward active region. How do I analyze in the forward active region? You start by assuming that the base emitter junction is forward biased. Find I base, so find the base current flowing here. Okay, find I base. Okay. Once you have found I base, you go back to calculate the collector current. Remember, in the forward active region, the collector current is related to the base current by beta. So I collector is equal to beta multiplied by the base current you calculated earlier. Once you have done that, you calculate VCE. VCE is equal to VCC minus IC multiplied by RC. I am pretty sure that if you do this calculation, you will find that VCE that you will be getting is a negative number, which is not physical. So if you assume the forward active region, you will end up with a contradiction. VCE in the forward active region must be positive, because this is 10, say this is whatever, 10 volts, whatever, and this is 0. So the voltage everywhere in the circuit has to gradually and slowly decrease from VCC to 0. So the collector voltage must be higher than the emitter voltage. So if you get VCE is negative, then this is not the forward active region. Then something is wrong in our analysis, our assumption is not right, then we must be in the saturation region. I collector and the I base are not related by beta DC anymore. Okay, as I explained earlier, one of the basic applications or the important applications of transistors is used as switches, and we use it as analog switch or a digital switch in digital circuits. And here, if I take a circuit like this one and I put 0 volts between the base and the emitter, because I have 0 volts here, I cannot have 0.7 to turn on this junction to make it forward biased. Then this means the base current is, the transistor is open circuit, base current is equal to 0, the collector current is equal to 0, so there is no current flowing here, then the voltage here is simply equal to VCC. And effectively, this is what we have in our circuit. It looks like an open switch. Between the collector and the emitter, there is an open switch. The whole supply voltage appears between the collector and the emitter, so VCE is equal to VCC. There is no current flowing anywhere in my circuit. So this is a transistor, the BJT as a transistor in the cutoff region. Of course, I also can use it as a transistor in the saturation region. If I apply sufficient voltage here to cause sufficient large current, it's relatively big current to flow into the base, then this will cause the transistor to saturate, okay? Meaning that VCE will be a small number, VCE sat, 0.1, 0.2, 0. I'm going to give you a number to use in calculations. It does not really affect the calculations that much. And in that case, I know what is IC sat flowing in. IC sat is simply equal to VCC minus VCE sat divided by R collector. Of course, the collector current and the base current are not related by beta anymore. They're not related by beta anymore. Okay, and in that case, because of the small voltage drop across the transistor, this is the equivalent circuit. It effectively represents short circuit. Of course, not short circuit really, there is some voltage, but it represents very small impedance between the collector and the emitter. So it represents like a closed switch. So I can find all this here. And here in this calculation, when I calculate this one, I assume that VCE sat small, so I neglected it. But really, the collector current is VCC minus VCE sat divided by RC. One other thing I would like you to remember here, if I apply, say, 5 volts between the base and the emitter, as shown here, say, then my saturation condition depends on the base current, but the base current will depend on RB. In order to get more current flowing into the base, you have to make RB smaller, because the smaller RB, the higher the value of the current, the more current flowing into the base, which means that the more the possibility the transistor is saturated. So RB has to be properly selected. Otherwise, you may be forcing the transistor to be in the forward active region, not in the saturation region. Because if this is big enough, then the base current will be small. It's not be sufficient to turn on to make the transistor saturate. So this is a very important thing to remember. This is a little bit different from the FETs. The FET transistors, we depended on VGS, and there is no gate current. While here, the base current is the one that determines everything, and the base current is really a function of RB. So the higher RB, the smaller the value of the base current. Okay, let's consider one more example here. We have a circuit. We'd like to determine what will be VCE when you have zero input voltage here. Would like to determine what is IB, minimum IB, to make this transistor saturate. As we agreed, you increase IB gradually and slowly until after a certain value, I collector cannot be equal to beta I base. It cannot follow this relationship, and the characteristics start to saturate. After that, actually, we enter the forward active region. But what I'm saying is, if the base current increases beyond a certain limit, then you are bringing this collector voltage lower and lower until VCE becomes small, and then the collector base junction becomes forward biased, meaning that we enter saturation. So to enter saturation, we must have some minimum value of IB to enter this saturation. And we're here assuming beta DC is 200. The last question is, we would like to determine the maximum value of RB to saturate the transistor if Vn is equal to 5 volts. As I explained to you, RB is very important here, because the higher the value of RB, the less the value of the base current. But we need a certain value of base current, minimal value of base current, in order to be able to be in the saturation region. So the first one is, if you apply 0 volts here, well, this is easy. If you apply 0 volts, then this junction cannot be forward biased, the transistor is off, and the VCE is simply equal to the 10 volts. What is the minimum value for IB to assume saturation? Well, we assume saturation, we assume VCE is equal to VCE sat. Find the I collector saturation, find the base saturation current, which the threshold needed for that, and then you will see you can determine what is the minimum value for IB to enter saturation. The last value is simply for RB, and this one is obtained from the relationship between IB and RB. So we can determine this last value. Okay, so this is more detailed solution. If Vn is equal to 0, VBE will be 0. Base emitter junction is reverse biased, transistor is off, no currents flowing anywhere. I base is 0, I collector is 0, no drop here, then VCE is equal to VCC is equal to 10 volts. To analyze the circuit assuming saturation region, as I said, you start by assuming VCE sat. So if you assume that the voltage between the collector and the emitter is VCE sat, which I'm going to take as 0 volts here. I'm going to give you exactly that number in midterms and finals and questions and so on. But here I'm assuming it is 0. So if I assume this voltage is small enough, I can neglect it. Then the current flow at the IC sat, the collector current at saturation, is VCC minus 0 divided by RC. So 10 minus 0 over 1K will give 10 milliampere. This 10 milliampere, if I divide it by beta will give me the threshold for the base current, and then I can move to determine the actual base current. So from the value of the saturation current, I determine then the threshold needed for the base current to be able to be in the saturation region is, we call it here IB minimum, which is IB saturation. It's IC sat over beta DC. Okay, this is our threshold. So we need at least 10 milliampere, which is the collector current, divided by 200. We need at least 50 microampere to be flowing into the base in order to be in the saturation region. Now, remember, in order to get this 50 microampere, our base has to be below a certain value, because the base resistance and the base current are inversely proportional to one another. So our base, we know that the base current is simply equal to this input voltage minus VBE divided by RB, or RB is equal to Vn minus VBE over IB. In order to get 50 microampere flowing into the base, which is the minimum base current to be in the saturation region, we can put this minimum base current, and this will give me the corresponding maximum allowed value for RB. Remember, because this is minimum, this is going to be maximum. They are inversely proportional. So this is 5 volts, this is 0.7. I already calculated this one. It's 50 microampere. You will see that the maximum value of RB in order for this transistor to be saturated at 5 volts at the input is 86 kilo ohm. Okay, so if you go beyond that, then at this 5 volts, you cannot be in the saturation region, you'll be in the forward active region.